In this video, we're going to take a look at vectors, specifically calculating magnitude and direction. So for our first example, let's find the magnitude of the vector b, which looks like minus 5i plus 3j. So let's draw a little sketch of b to get a feel for this problem. B is traveling -5 units in the x direction. Okay, so 5 units left, and it's traveling 3 units in the y direction. So up to +3. So our vector is starting at the origin, traveling over to the point -5, 3. So there's a sketch of our vector b. Now whenever we want to calculate the magnitude of a vector a, and remember magnitude, just another way of saying length. Okay, so let's say we want to calculate the length of any vector a that's in the plane. What we can do is just visualize a right triangle. So we can think about the x component of our vector a, we could call it ax, and the y component of our vector a, we would call that ay. And the hypotenuse here would just represent the length of our vector. So we've got a nice right triangle. And the Pythagorean theorem tells us how to calculate the magnitude of our vector. Our magnitude a will be the square root of ax squared plus ay squared. So that is the general formula for magnitude of a vector as long as our vector is in the plane. All right, so to answer the question then, the magnitude of this particular vector b, well, in referring to the magnitude, we usually just drop the arrow sign there. So the magnitude would be written b, and to get that magnitude, we're going to take the square root of our x component squared plus our y component squared. So this gives us the square root of 34. So this magnitude here, that's just another way of saying length, as we pointed out earlier. So we're saying the length of our vector b is root 34. Okay, now let's talk a little bit about the direction of a vector. The direction of any vector a that's in the plane. Well, let's imagine a vector that is in the first quadrant. So this would be our x-axis here, our y-axis, and let's say our vector is going over like this. So we could draw our x component of our vector, we could draw our y component of our vector, and this hypotenuse here would represent the length of our vector, just like before. Now let's say that we're interested in finding this angle theta here. Well, if we think back to trig, tan theta is going to be opposite over adjacent. So it'll be ay over ax. And then to get theta, we can apply arctan to both sides of this equation. So the arctan function will come along, undo tan, and we'll have theta equals arctan of ay over ax. Now in this situation here, we imagine that our vector was in the first quadrant, so this little calculation here for theta works perfectly. But there is a little bit of a catch here, because arctan is restricted in the kinds of angles that it can return to us. So arctan only gives angles that are between -90 degrees and 90 degrees. That's the way the arctan function works. So we need a formula that's a little bit more general to help us find the direction of any vector. direction is going to look pretty much like arctan of our y component divided by our x component. But to make sure that we're able to get all possible angles here, we may need to add 180 degrees to this answer. So this is how I like to think about the general formula. The direction is arctan of our y component divided by our x component, and we may need to add 180 degrees depending on our particular vector. So as a little warm-up here, let's try to understand why we have this plus 180 degrees on here in this formula. So little warm-up. Okay, let's say we have an angle theta so that tan theta is equal to 1. So we might try this approach here on our calculator and just say, well, theta then is going to be arctan of 1. That's one possibility. And if we try this on our calculator, or you might remember from trig, arctan of 1, 45 degrees. Okay, well, this is not the only possibility. The other possibility is that theta is actually 45 degrees plus 180 degrees. So in fact, theta could actually be 225 degrees. So to convince ourselves that this is true, probably the fastest way to do that is just try tan of 45 degrees on our calculator. Yep, that's equal to 1. And let's check that tan of 225 degrees is also equal to 1. Yeah, it is. So just being told that tan theta is equal to 1 does not actually tell us what our angle is. It gives us a pair of possible angles. Okay, well, let's try to understand a little bit further why there are really two possibilities for theta. So if we think back to our cast rule from trig, I know it as a cast rule. Some students remember some kind of saying like all students take calculus or something to that effect. What this represents is where the various trig functions are positive. So all three of sine, cos, and tan are positive in the first quadrant. Only sine is positive in the second quadrant. Only tan positive in the third quadrant, and it's just cos that's positive in the fourth quadrant there. So if someone tells you that you've got some angle so that tan theta is positive, there are really two possibilities for where theta could lie. Okay, maybe we're in quadrant 3 where tan is positive, but maybe we're in quadrant 1 where all three of our basic trig functions are positive. So really two options. Theta could be in either quadrant 1 or quadrant 3. And a similar thing happens if someone tells you that tan theta is negative. Now suddenly there are two options. If tan theta were negative, we could be over here in quadrant 2, or we could be in quadrant 4. So just being given a particular value of tan theta, unfortunately, it's not enough to know exactly where our angle lies. But the really nice thing about tan theta, or the function tan, is that if tan theta is positive, one of the options is over here in quadrant 1. The other option is exactly 180 degrees bigger. So that's what allows us to come up with our general formula here, that to get the direction of a vector, we're just going to go arctan of its y component over its x component, and we'll need to add 180 degrees to that as well. So that gives us two possible directions. And then to determine whether we really need to do this or not, we just draw a quick sketch of our vector and see which one matches our picture. So with that whole explanation over with, let's focus on a typical example that we might have to do here. We're going to think back to our original vector b that we had at the beginning of the problem. It was minus 5i plus 3j, and we're going to find the direction of b. All right, so according to our general formula here, our direction of b is going to be arctan of the y component, so 3, divided by the x component. And we just need our brackets there to make sure that arctan applies to this entire fraction. Okay, and to get the correct direction, we may need to add 180 degrees to this. So we'll think about both the possible angles here. So if we grab our calculator, arctan of 3 divided by -5 comes out to about -30.96 degrees. So it's possible that's our answer. Also possible that our true answer is really 180 degrees bigger than that. So to decide which one is the real direction, let's draw a little sketch. Well, minus 30-ish degrees is down here. So minus 30.96 degrees looks like that. The other option is that maybe our vector lies in the complete opposite direction. So if we actually take minus 30.96 degrees and add 180 to that, let's write this down here, then what we end up with is an angle that looks like 149.04 degrees, or just about 149 degrees. So one of these two answers is the correct one. To decide, this is where a sketch comes in super handy. Just very quick sketch of what our vector b actually looks like. Remember, it was going -5 units in the x direction, 3 units in the y direction, so it's looking like this. So just from matching this to our sketch, -30-ish degrees or -31 degrees, that's not looking like our vector. Our vector is going in the other direction, so it's this 149 degrees that looks right. So that is how we solve the problem. We say direction is 149.04 degrees.